So, uh, by the way, okay, I forgot to mention one thing. Okay. You can see that, okay, all the autoencoder in the training here, you can see the training, the input is extract, right? And the ground truth is also extract. I mean, so really like autoencoder, for autoencoder, I mean, it does not require label. Okay, same thing goes for this one. Okay, you can see extract. The input is used as the label. Okay, so because of that, okay, I mean, the autoencoder, okay, can be used for unsupervised retraining. Okay, assume that in chapter 11 we talk about like for difficult job. Okay, if you do not have a lot of labeled training data set for a very difficult job, okay, one solution is to find a neural network that performs similar tasks and then do a transfer learning, right? Basically, we use the most of that model, okay, the lower layers, okay, of that model, okay, and then just replace the top few layers, or add like 1 or 2 layers, and then do the proper training, okay. So the transfer learning does not require a lot of labeled training data set. Okay, so that's good. Okay, so this makes it possible to train a high performance model using little training data. Okay, because the neural network won't have to learn all the low level features. Okay, so but a lot of time, okay, if you don't have a model that deal with like a similar task, what do you do? Okay, if you have a large data set, but most of the data set are unlabeled. This is actually like unfortunately, okay, the case for most of like the situation, real world situation. Okay, so what we can do is, okay, we can train a stack autoencoder using all the data. Okay, we could train a stack autoencoder without any label because, as I just told you, okay, I mean the label for the autoencoder will be exactly just like the input, right? So you really don't need to have any, do any labeling, okay? And you can train a stack autoencoder with a lot of unlabeled data, okay? And then your autoencoder will learn all those features, okay? And then, okay, what you can do is you can reuse part of your, coding encoder, part of your encoder, okay, to construct your own model, okay, just like transfer learning, okay. You probably need to also add like a few new layers on top of the coding layer, and then go through the transfer learning process. Okay, of course we still need to have a data set with a little bit of data set with label. Okay, for the transfer learning. Okay, so it's going to be something like this. You can see this figure. Okay, so we say we use a large amount of labeled, unlabeled data to train this autoencoder. Then what happens is that you can reuse this encoder. Okay, you just copy this encoder. And then add maybe 1 to 2 new layers on top of that. Okay? And then go through the transfer learning process. Remember what transfer learning process is? You need to, lock the weight of the low layers. Okay, freeze the weight, remember? And then use a little bit larger learning rate, okay, to train maybe the weights in the new added layers for few epochs. And then, okay, after that, okay, you unfreeze maybe the top few weights of the top few layers. Or if you have enough data with a label, then you unfreeze all of them. Okay, and then use a smaller learning rate to tune your model. Okay, so this is like a transfer learning. I mean, this is important. Okay, I mean, try not to. Okay, I just copy these few layers, and then I add 1 more layer, and then I just train it just like a regular model. Okay, then it's not going to. You are going to ruin the whole model. Okay, because the regular learning rate is going to tune not only this newly added layer, but also the weight in the lower layers, which you shouldn't be done. Okay, you shouldn't let that happen, because what in the transfer learning, what happens is that you want to reuse the feature you learn from the lower layers. So you don't want to, at least change too much in the lower layers. At most, you only want to tune a little bit. Okay, so that's I was surprised, one of my graduate student, when she was doing a project, and I told her to, okay, you should use transfer learning, and then she just didn't freeze the weight of the lower few layers, and just train, just add 1 or 2 layers, and then train the whole model, just like a regular model. Right? Basically, you lost the advantage of transfer learning completely. Okay, so that's not what it's supposed to do. Okay, but anyway, okay, so this is unsupervised retraining using autoencoder. So you could use a lot of unlabeled data set to train autoencoder, and then reuse the encoder, kind of like a transfer learning. Okay, we actually talked about this a little bit in chapter 11, but we just didn't, we didn't go very deep at that time because autoencoder was not covered in that chapter. Okay, problems. Okay, so this is like what you can do. Okay, so having plenty of unlabeled data and little labeled data is common. Okay, it's common. I mean, as I said, it's like it happens all the time. Okay, so building a large unlabeled data set is always cheap. Okay, for example, you can download millions of images from the internet. Okay, just write a very simple code. Okay, it's not like the old days. In the old days, we keep photos in a book and keep it for the private viewing. But nowadays, everybody want to post the photo online. Okay, so a lot of data are actually available online. Okay, nowadays. So but labeling those images, okay, such as classifying them as cute or not. Okay, so this is just an example. I mean, a lot of times it depends on what type of task you are doing, okay? But anyway, okay, the labeling will be very tedious and take a lot of, labeling work, okay? So it can only be done reliably by humans, okay? So labeling in this instance is time consuming and costly, so it's normally to have only a few thousands of human label instances, okay? So this is like, this is common, but only a few thousand human label instances normally is not good enough for to train a model from the ground up, okay, in the deep learning. Okay. For deep learning, you normally will need at least tens of thousands of label data set to train a model. Okay. Sometimes you even need like hundreds of thousands label instances. Okay. But anyway, so a lot of time the difficult thing is to get the label data set, a huge label data set, and that label data set are trustworthy. A lot of times you just don't have that luxury. Okay, so there's nothing special about the implementation. Just train autoencoder using all the training data. I think we have already talked about how to write the code for the stack autoencoder. So you just use all the data to train that stack autoencoder. Okay, and then you use the encoder layers to create a new network. That's it. So this is nothing new. Okay, so let's look at a few techniques for training stack autoencoders. Okay, because after all, training stack autoencoder, especially when you have many layers, okay, sometimes it could take more time. Okay, so are there like some techniques that can help us to train the stack autoencoder more effectively? Okay, the first one is time weight. Remember, I just told you the autoencoder is symmetrical, right? The encoder and the decoder are symmetrical. If the encoder looks like this, then decoder must look like you just have the encoder just like a flip it, okay, around, and I told you actually you can go even more, even further than that. Okay, it's not just symmetrical. Okay, even their weights could be tied. Okay. After all, think about this. What is autoencoder? What is the job for the encoder? The encoder is to convert the data into coding, right? Convert the data into coding, or later today, whatever you want to say. Okay. So it convert data to the coding. So decoders convert the coding back to the data, right? So the job is exactly the opposite, right? So what happens in the coding, in the encoder? What happens in the encoder should be reversed in the decoder, right? Right? Conceptually, the decoder's job is the inverse of what should be done in the encoder, right? So because of that, okay, you could tie the weight of the encoder and the decoder, because if they are doing exactly the opposite thing, then pretty much you can use the same set of weight. It's just like you just need to arrange them so that they work like the opposite manner. Okay, so connection weight of the L layer. Okay, so the layer 1, okay, is the first hidden layer. Layer N/2 is the coding layer, and layer N is the output layer. Okay, let's assume this is the case. Then the decoder layer weight can be defined simply as Wn minus L plus 1 equal to WL transpose. Remember this, there's a transpose here. Okay? The reason to have a transpose is because we want to do it in the opposite manner, right? So this transpose basically helps us to do exactly opposite. Okay, this layer should do exactly opposite of layer L. Okay, so the weight of this in this layer should be WL transpose. Okay, and this time weight, okay, effectively, okay, cuts the amount of parameters that need to be trained by approximately half, right? Because, well, no, originally you train the whole autoencoder. Now you need to pretty much only train the encoder. The decoder weights are pretty much just the reverse of encoder, right? So you don't need to train that. Okay, they are pretty much the same, right? Pretty much the same. So because of that, so the number of parameters that need to be trained is significantly reduced, okay, by half, okay, approximately half. This not only speeding up the training, but also limiting the risk of overfitting. Okay, the smaller amount of parameters in the model means the less chance for this model to overfit. Okay, so this is a very good thing to do. Okay, very good thing to do. So how do we tie the weight? Okay, so we need to define the custom layer. Okay, this custom layer, okay, basically, okay, well, we call this dense transpose. This is like a subclass of the layer class. Okay, so I think I will just keep the detail here. I mean, you can check the detail here. So it shouldn't be that difficult to understand. But basically, like here, okay, you can see we intentionally create the first hidden layer outside of the encoder. We call that layer, okay, with 100 neuron activation function to be 0 as a dense 1. And the second hidden layer, we call dense 2, okay, 30 neuron and activation to be 0, okay. So in our encoder, okay, so this one is also dealing with the virtual MNIST, okay. So we try to use the running example. So basically, we try to stick with the same example. Okay. So you can see the input is 28 by 28. We flatten that. So it's a 784, and then we have to go through the first hidden layer, the second hidden layer. So this is our encoder. The coding will be 30. Okay. Contains 30 numbers. Okay. So and you can see we call this tie encoder, and the tie decoder will be transpose, dense transpose. Here, the dense 2. Okay, we put dense 2 here. Okay, meaning we want this layer to have the same number of neurons in the dense 2. But not only that, we want the connection weight of this layer to be tied with this dense this dense 2 layer. And of course the activation is still 0. And for the second layer in the decoder is, again, we want to tie this weight use sigmoid as activation function, and then we reshape this one-dimensional output to be two-dimensional. The other parts are basically the same as like the previous discussion. Okay, and we treat each pixel as like a binary classification. So the loss function will be binary cross entropy. Okay, just like we discussed in the previous example. Okay, so this model achieves a very slightly lower reconstruction error than the previous model, with almost half the number of parameters. Okay, not only this reduces the training time, it actually performs slightly better. Okay, so this time weight is a good thing to have. Okay, and also okay, if your data set is not big enough to train the whole autoencoder in one shot, then you could train one autoencoder at a time. What do I mean? Okay, I mean what does that mean by one autoencoder at a time? Okay, that means like we gradually like stack up the autoencoder to make it like deep. Okay, but each time you only train a very shallow autoencoder. Okay, to be honest, this technique is used very seldomly recently because, as I said, like most of the time, it's not difficult to get a lot of unlabeled training data anyway. Okay, I mean, remember, like, when you train the autoencoder, you don't need to have label. So to get a large amount of unlabeled training data, it's not too difficult. Okay, it's not too difficult. Okay. So you can train the whole autoencoder in one shot. But sometimes, okay, at least like in some paper, especially like in the old paper, in some old paper, you will still be able to see like this approach. Okay, this approach is also called like a greedy layer-wise training. So what is it? Okay, so you can see this is like a shallow autoencoder, right? We have input layer, hidden. This hidden one layer is the it will create a coding, and then output layer, right? Very simple, right? Okay, with such a simple structure, okay, such a shallow structure, okay, even if your data set is not much, you can still train this shallow autoencoder, right? And then you train this one, the middle one. Again, you have input, you have output, and your hidden one, okay? Obviously, I mean, the middle autoencoder is also a very shallow one, right? Okay, and this one also does not require much data to train, okay? And then you somehow you can combine these two to form a deeper autoencoder. Okay, I mean the picture just say like that, but actually it's more complicated than what is shown in the picture. Okay, so first, okay, to train this one is obvious. I mean, let's say we use facial MNIST data set. Okay, so the input will be facial MNIST data set. The output will be facial MNIST data set. No question about that. Okay, so the training of this is easy. But if you want to train this one, and then you want to combine these two together, then it's a little bit more complicated than what you may think. Okay, this layer, this is input, which will not be used. okay, the hidden one will be used here. The output is going to be used here, right? So this output, because this output will be used here, so this output has to be of the same size as this hidden one, right? So this output, okay, has to be of the same size as hidden one. That's the first thing. That's why, okay, they are labeled as blue color. So because of this, because this is labeled as, I mean, has to be the same size as this one, you could imagine this one has to be also exactly that size, right? Because we are talking about autoencoder here anyway, right? So if the output is, I mean, layer has, let's say 30 neurons, this one has to have 30 neurons as well, right? Not only that, because think about this. This hidden layer, this hidden one, this blue, this red layer is going to be placed here, right? This layer is going to be placed here. So imagine what input is going to receive. It's going to receive input from the output of hidden one, right? So actually, okay, this hidden one output, okay, or let me put it this way, the coding, originally we use like the MMST data set to train this model, this autoencoder, right? Okay, but this one, okay, this one, the one this output, okay, this layer output is the coding of this autoencoder, right? So the coding that output in here, okay, will be used as the input for this middle autoencoder. So this input is going to be coding. Of course, the label will also be the coding. Okay? So we use the coding of whatever you call it, I mean, the output hidden one here as the input here. And the label will also be the same thing. Okay? And once we finish training this one, then we copy, okay, hidden one to here, we copy hidden one to here, this output to here, this output to here. Okay, then we form this stack autoencoder. Okay, so this is training one autoencoder at a time. Probably it should be rephrased as training one shallow autoencoder at a time. Okay, because each autoencoder that we train during the process is shallow, is very shallow. But eventually we try to combine them to form a deep autoencoder. But be very careful, okay? The first one, we use just regular data. But starting from the second one, we are not using the regular input. We're using the middle, the information in the middle as the input here. Okay? We could get the coding. We could obtain the coding of this autoencoder very easily, right? Remember we did that in the previous example. For example, for the facial MIST, we get those 30 dimensional vectors, right? Before we put it into the dimensionality reduction algorithm. Remember? So this is not very difficult, right? Very easy to do. And then we use that as input and label to train this one. Okay, and obviously, this process can be repeated. In other words, okay, this one is like autoencoder with 5 layers. If you want an autoencoder with 7 layers, you could insert a third shallow autoencoder here, right? But that shallow autoencoder is going to be trained using the coding of the second autoencoder. And you are going to have to put the third autoencoder, the layers, at the appropriate place to form that 7-layer autoencoder. Right? Okay, so this is like how in the old days, okay, when there's no internet, okay, there's no World Wide Web, okay, there are not so much free and free data available to the researchers. So this is how the autoencoder can be trained. Okay. So I think I will already explain what happens in this example. So I will skip this. Okay. So actually, okay, the similar process, okay, was used. Okay, actually Geoffrey Hinton, I think I talked about this earlier, okay, in chapter 11. Okay, Geoffrey Hinton, okay, tried to use, he actually used a certain unsupervised pre-training to create his first deep neural network model back to the 2006. Okay, but at that time, okay, his finding, okay, actually triggered the third wave of AI actually. But the more important thing is that, okay, at that time, he was not using autoencoder. He was using restricted Boltzmann machine. This is a different stuff, okay. But the restricted Boltzmann machine, okay, abbreviated RBS, okay, can also be trained using without label. Okay, can also be trained without label. So he used this RBS, okay, to train to do this unsupervised pre-training, and then use that to create his deep model. Okay, but a year after his research, okay, Yoshua Bengio, okay, team, they actually used autoencoder to show that the same thing can be achieved by the autoencoder. RBM is very difficult to deal with. Okay, RBM is like for every training, you need to wait until the restricted Boltzmann machine to stabilize before you can do the next step. So the training is even more complicated than autoencoder. Okay, if you are interested in the RBM, okay, the appendix E in the textbook, okay, talk about that. But I will not cover that in this class. It's because nobody uses restricted Boltzmann machine nowadays because it's just difficult to use. It's just too difficult to use, and the current deep learning model can do the task much better than what restricted Boltzmann machine can do for you. Okay. But anyway, okay, this is just the history. Okay, just some story for you. Okay, so. But this technique, okay, the really layer-wise pre-training, okay, this approach, as I said, okay, as the unlabeled data set become more and more easy to obtain on the internet, on the World Wide Web. Nowadays, people start to just train the whole thing, together. Well, the time weight help. Okay, time weight help, but you really don't need to train one shallow autoencoder at a time. This is probably not what we do nowadays. Okay, so autoencoder were not limited to dense networks. Okay, you also build convolutional autoencoder or recurrent autoencoder. Okay, so let's have a look. Okay, so if you are dealing with image, okay, then obviously like the dense layer, okay, do not work well for image, right? I mean, we discussed that very a lot in the convolutional neural network chapter, right? I mean, even in our example, we discussed like autoencoder, for like a facial MMST, which will happen to be an image data set, right? But the facial MMST is a very small image. I mean, it contains small images only, right? Unless the image in the data set are small. Otherwise, you don't normally use dense layer to deal with image. It's because it takes too much memory. Okay, it's not efficient, right? We talked about this earlier anyway. So instead, we prefer to use convolutional layer, right? And even pooling layer, right? So we could use convolutional layer and pooling layer to create autoencoder without any problem, okay? And it's just like, how about in a decoder? I mean, in the encoder, because normally in the encoder, we will do the subsampling. Because in most of the autoencoder, the coding size is smaller, right? The coding size is smaller. So in the encoder portion of autoencoder, normally the process is a subsample. So the similar approach that we have seen in the convolutional layer is when we are doing the subsampling. We are trying to, the image, or how we should say, like feature maps, getting smaller and smaller, right? I mean, it still applies, okay? But how about decoder? For decoder, we are going to do, I mean, the image or the feature map has to grow, right? We need to grow from the coding back to the image, right? So what do we do? Okay, something that we have learned, okay? Remember we talked about super resolution. Super resolution. I mean, if you guys still remember, we talked about super resolution in the CNN chapter, okay, which allows us to enlarge your feature maps. And that type of layer is called the transpose convolution layer. Okay, so transpose convolution layer could be used for like decoder portion of the autoencoder. Okay, if you want. Okay. So well, it's a break time. So let's take a 10 minutes break. When we come back, we will discuss like this.